Bismillahirrahmanirrahim. Today we will discuss about uh, two methods of detection in orthogonal frequency division multiplexing and some other trade-offs that we have to cater while we are considering the cyclic prefix and the delay spread when we are using the OFDM. So this is week number 13 and lecture number 29. So how do we detect symbols in OFDM? There are many methods, but we will be discussing only two methods. One method is to employ zero forcing across each subcarrier. So this is the equation of the subcarrier model of the OFDM system, in which y is the received symbol at the subcarrier k, that is equal to the h at subcarrier k and x at subcarrier k plus n at subcarrier k. This is the noise across the n subcarrier. So estimated symbol at carrier k is given by yk upon hk, where hk is estimated before by transmitting pilot symbols. So when we do this, so we will have the estimated xk would be equal to xk plus some noise factor, which is also divided by hk. So this is n dash of k. So depending upon the noise and the signal to noise ratio, we will have a good estimate of xk or a bad estimate of xk or an average estimate of xk. The second thing is the match filter detection. Match filter detection, we multiply the received symbol at subcarrier k with the conjugate of h of k, which results in hk square into xk plus n dash of k, where n dash of k is basically hk into n of k. Now this thing can be employed for BPSK detection. So this is called match filter detection. Now we will talk about OFDM trade-offs. We used cyclic prefix in OFDM to avoid intersymbol interference and interblock interference. What was cyclic prefix? We copy the symbols L minus at least n minus 1 symbols as a prefix to the original block of symbols. So the minimum length of this block, cyclic prefix block required, is L minus 1. Depending upon how much there is delay spread, we can have the CP, which is greater than N minus 1. So to avoid intersymbol interference completely, we have to have CP length which is greater than the delay spread of the channel. So simply making CP long or repeating the symbol does not constitute information. So hence the effect of addition of long CP is a loss in overall throughput of the system. So if we calculate the loss in efficiency, that would be equal to CP length divided by the total OFDM symbol length. So CP length is given by L minus 1, the total OFDM symbol length is given by L minus 1 plus n. So that tends to 0 as n goes to infinity. So when n is large enough or the subcarriers are large enough, so this implies lower loss in the throughput. So the loss goes to 0 when we have n is greater, quite large, because when n is quite large, so this term goes to 0, because this term is n minus 1 and this term is kind of infinity, so it goes to 0. Now as n increases, the OFDM symbol time also increases, as depicted by this equation. N divided by b, if n is large, so n over b will also be large. So as n increases progressively, we have a smaller fraction which is affected by intersymbol interference. So smaller fraction of the total symbols, they are affected by ISA. So increasing the L results in increasing OFDM symbol time, which comprises for the intersymbol interference arising out of delay spread. So as n increases, the decoding delay of the system increases. Increasing n is good thing because it avoids ISI at a large extent, but the problem is that increasing the symbol time also increases the decoding delay, which we don't require. Hence there is a trade-off for increasing n versus the decoding delay. So we can have a nice framework to get insight into the CP. Now we know that NCP multiplied by TS is greater or equal to TD. NCP is greater or equal to TD of TS. So 1 over TS is equal to B. TS is a symbol time. Delay spread is given by 1 over 2 into coherence bandwidth. So here we get B into 1 over 2 BC, or NCP is greater than B over 2 BC. So what is NCP? NCP is the number of symbols which constitute the cyclic prefix. So the good thing is that we should have NCP that should be greater or equal to B over 2 BC. BC is the coherence bandwidth and B is the bandwidth of the system which comes from the symbol time. Now for efficiency we need to have N greater than NCP, which is greater or equal to B over 2 BC. So this means that N should be quite large, greater than B or BC. Now this is the criteria to select the number of subcarriers. N is the number of subcarriers. Or coherence bandwidth should be quite large than B over N. B over N is the bandwidth of each subcarrier and BC is the coherence bandwidth. So this means subcarrier bandwidth should be smaller than coherence bandwidth. That means that each subcarrier experiences frequency flat fading. So a well-designed OFDM system converts a frequency selective fading channel into a set of parallel narrowband flat fading channel across the subcarriers. Example is of a fixed mobile WiMAX system, OFDM system, in which N is equal to 256 subcarriers. So the subcarrier bandwidth is equal to 15.625 kilohertz. So B over N is equal to 15.625 kilohertz. So 15.625 kilohertz is quite smaller than coherence bandwidth, which is normally around 200 to 300 kilohertz. So each carrier experiences flat fading. So from here we can calculate B. B turns out to be 4 megahertz is the transmission bandwidth. So OFDM symbol time without CP is equal to N over B. So N over B is equal to around 64 microseconds. So OFDM symbol time is 64 microseconds. Standard CP is probably most of the time approximately equal to 12.5% of the symbol time. So if you put the values 12.5 divided by 100 into 64 microsecond turns out to be 8 microseconds. So this is the duration of the CP symbol time. So the total time is basically 64 plus 8 is equal to 72 microseconds. Okay. So total OFDM symbol duration with CP is equal to 72 microseconds, 62 from plus 8 microseconds, basically this 8 microseconds is put it here as a prefix. So now we can calculate the number of samples in CP. So CP duration divided by sample time is equal to 8 microsecond divided by 1 over B is equal to 8 microsecond into 4 into 10 to the power 6 is equal to 32 samples. So we have 32 samples as a prefix and then we have 256 samples. So total samples would be equal to 288. So 32 divided by 288 is equal to 8 microsecond divided by 72 microsecond is equal to 11.1%. Thank you.